A locomotive, weighing 30 tons, being hauled across a frozen lake. The ice is 3 feet thick, but you're still standing on frozen water with 60,000 pounds of metal above you. The ice creaks and groans with every movement. Water seeps up through small cracks, and you're a mile from shore in any direction, pulling this monster with teams of horses across a surface that could break and plunge everything, locomotive, horses, men, into water so cold you'd be dead in minutes. This was how America built railroads in winter. The frozen rivers and lakes weren't obstacles, they were highways. Natural roads that appeared every winter, strong enough to carry millions of pounds of supplies, and then vanished every spring. Rails, ties, locomotives, construction equipment, all of it transported across ice. Because when you're building a railroad through wilderness, there are no roads to haul supplies. So you wait for winter, when the lakes freeze solid, and you create temporary roads that will disappear in April, but get the job done by March. This was railroad construction in the northern United States and Canada from the 1850s through the early 1900s. Railroads were being built through regions with no existing transportation infrastructure. The Great Lakes region, the Canadian prairies, the forests of Wisconsin and Minnesota. These areas had lakes and rivers, but few roads. During summer, the lakes were barriers that required expensive ferries or bridges. But in winter, those same lakes became assets. They'd freeze solid enough to support incredible weights, and railroad construction companies learned to use them as supply routes, moving materials across ice roads that would have been impossible to transport any other way. Could you really haul a 30-ton locomotive across frozen lake ice? Could teams of horses pull loaded wagons carrying tons of steel rails over ice roads miles long? And could you do this safely, knowing that a breakthrough meant death for everyone involved? The answer is yes. The evidence exists in photographs showing locomotives and rail cars on lake ice, in construction records documenting supplies moved over ice roads, and in the railroads that were built using these techniques. Before we get to how it was done, you need to understand why frozen rivers and lakes were so valuable for railroad construction. Because this wasn't just about convenience. This was often the only practical way to move heavy materials to remote construction sites. A railroad requires enormous quantities of heavy materials. Steel rails weigh hundreds of pounds per length. A 30-foot rail might weigh 400 pounds. A mile of track requires over 350 rails, which is about 70 tons of steel just for the rails. Then you need ties, 14,000 wooden ties per mile, each one weighing 100 to 200 pounds. That's another 700 to 1,400 tons. Add in the equipment, tools, locomotives, and support materials, and you're looking at thousands of tons of material that need to be delivered to every mile of railroad being built. In established areas with existing railroads or good roads, you could transport these materials relatively easily. But for railroads being built through wilderness areas, transportation was the primary challenge. There were no roads. The terrain might be swampy or heavily forested. Rivers might be unnavigable. During summer, the only option was often to build temporary roads or use rivers where possible. But both of these were expensive and slow. Winter changed everything. When rivers and lakes froze, they became highways. The ice provided a smooth, level surface. You could go straight across a lake that would take miles to circumnavigate on land. The frozen ground made swampy areas passable, and if the ice was thick enough, it would support massive loads that would be impossible to move any other way. The ice thickness required for safe travel depended on the load. For a person on foot, 6 inches of ice was adequate. For a horse and light sleigh, 12 inches. For a loaded wagon with a team of horses, 18 to 24 inches. For extremely heavy loads, like locomotives, you wanted 36 inches or more. The relationship between ice thickness and safe load was well understood by teamsters, who made their living hauling goods over ice roads. The rule of thumb was that ice thickness in inches, multiplied by itself, gave you the safe load in hundreds of pounds. So 12 inches of ice could theoretically support 14,400 pounds. 12 times 12 equals 144, times 100 is 14,400 pounds. This was a rough guideline that provided a safety margin. In practice, teamsters would be more conservative, especially with valuable or dangerous cargo. The physics of ice load bearing is complex. Ice is not a perfectly uniform material. It contains air bubbles, impurities, and structural variations. The strength depends on temperature, with colder ice being stronger. Ice at 0 degrees Fahrenheit is significantly stronger than ice at 30 degrees. The loading rate matters. Sudden impacts stress ice differently than slow, steady loading. And the distribution of weight is critical. A concentrated load creates more stress than the same weight spread over a larger area. The type of ice also mattered. Clear blue ice, formed from direct freezing of water, was strongest. White ice, formed from frozen snow or slush, was weaker. A layer of white ice atop blue ice reduced the safe load capacity. Experienced ice road operators could assess ice quality by appearance, sound when struck with an axe, and the way it responded to drilling. The temperature fluctuations during an ice road season affected operations. A warm spell could weaken ice dramatically. A cold snap could strengthen it, but also cause contraction cracking, long cracks that formed as ice contracted in extreme cold. These cracks didn't necessarily mean the ice was unsafe, but they had to be evaluated. A crack filled with refrozen water was strong. A crack that remained open was a weak point. The phenomenon of pressure ridges, where ice sheets had buckled and pushed up, created both obstacles and sometimes opportunities. A pressure ridge was an area of thicker ice, potentially safer for crossing, but it also created a rough surface that had to be smoothed or circumnavigated. The forces that created pressure ridges were immense. Ice expanding and contracting with temperature changes could generate pressures that buckled the ice sheet into ridges 10 or 20 feet high. The monitoring of ice conditions was constant during operations. Workers would drill test holes every few days along the entire route. They'd record ice thickness at each point. They'd watch for changes in surface appearance that might indicate underlying weakness. And they'd pay attention to sounds. Ice makes constant noises as it expands, contracts, and shifts. Experienced workers could distinguish between normal ice sounds and sounds that indicated potential problems. The testing of ice thickness was done by drilling or chopping through the ice at intervals along the planned route. Workers would drill holes with augers and measure the ice thickness. If the ice was inadequate in any spot, the route would be adjusted to avoid that area or delayed until more freezing occurred. The ice thickness could vary significantly even within a small area. Underwater springs, currents, or variations in snow cover could create thin spots. The underwater topography affected ice formation and strength. Shallow areas froze earlier and typically had thicker ice. Deep areas froze later and might have thinner ice. Areas with strong currents might not freeze at all, or might have deceptively thin ice. Before establishing an ice road, the underwater conditions would be studied to identify potential problem areas. The wind effects on ice were significant. Wind moving across open water before freeze-up would create waves that resulted in rough ice formation. Wind after freeze-up could clear snow from some areas while creating drifts in others, affecting both ice thickness and surface conditions. Strong winds could also cause ice movement. The entire ice sheet might shift on the water beneath it, opening cracks or creating pressure ridges. The preparation of ice roads required work beyond just waiting for ice to freeze. The route would be surveyed and marked with poles or flags. Snow would be cleared from the ice surface. Snow acts as insulation and prevents further ice thickening, so clearing it allowed the ice to freeze deeper. In some cases, Water would be spread on the cleared ice to create an additional, smooth ice layer. The road would be tested by sending light loads across first, then progressively heavier loads as confidence in the ice grew. The transportation of rails over ice roads used specially constructed sleighs designed for heavy loads. A rail sleigh might be 20 to 30 feet long with massive runners. Multiple rails could be stacked and tied to the sleigh. A team of 4 to 8 horses could pull a sleigh carrying perhaps 2 to 3 tons of rails. The horses would be driven carefully, keeping a steady pace without sudden movements that might stress the ice. The construction of ice road sleighs was specialized work. The runners had to be wide enough to distribute weight, but not so wide that they created excessive friction. Typical runners were 6 to 8 inches wide and might be 4 inches thick. The runners were shod with metal on the bottom to reduce friction and prevent wear. The spacing between runners was calculated to provide stability, typically 4 to 6 feet between runner centers. The bed of the sleigh was a heavy wooden framework that connected the runners and provided the platform for the load. The framework used massive timbers, 4x6 or 6x8 inch beams, assembled with mortise and tenon joints reinforced with iron bolts. The bed had to be rigid enough not to flex under load, which could create uneven ice loading and potential failure. The total weight of a large rail sleigh without load might be 2,000 to 3,000 pounds. The connecting of horses to sleighs used specialized harnesses designed for heavy pulling. The horses would be hitched in teams, pairs of horses side by side. Multiple pairs would be hitched in tandem, creating teams of 4, 6, 8, or more horses, depending on the load. The harness arrangement distributed the pulling force evenly across all horses. The lead horses would take about 30% of the load, the middle pairs about 25%, and the wheel horses, the pair nearest the sleigh, about 15%. This distribution accounted for the different physics of pulling from different positions. The loading of rails onto sleighs required both muscle and technique. Rails weighing 400 pounds each couldn't be simply lifted by manpower. The technique was to use a loading ramp or simple crane arrangement. Rails would be rolled onto the sleigh bed and positioned lengthwise. Multiple rails would be stacked and tied securely with chains or heavy rope. The stacking pattern was calculated to keep the center of gravity low and centered on the sleigh. An improperly balanced load could cause the sleigh to tip during travel or create dangerous stress patterns on the ice. The tying of loads used techniques developed over years of experience. Chains would be passed under and over the rails, then tightened with come-along devices or by levering with pry bars. The chains had to be tight enough that the load couldn't shift, but not so tight that they damaged the rails. The securing work might take an hour or more for a large load, but it was critical. A shifted load could cause disaster on the ice. The horses used for ice road hauling were carefully selected and trained. Not every horse could handle ice road work. The horse had to be calm enough not to panic on the ice, strong enough to pull heavy loads, and intelligent enough to respond to commands in difficult conditions. The breeds used were typically heavy draft horses, Percherons, Belgians, Clydesdales, or Shires. These horses might weigh 1,600 to 2,000 pounds each and could pull loads several times their own weight. The training of ice road horses started with gradual exposure to ice conditions. A young horse would first be walked on ice without a load, then hitched to a light sleigh, then progressively heavier loads, as the horse demonstrated comfort with ice travel. The training might take an entire winter season. A fully trained ice road horse was valuable, potentially worth several $100s, which was substantial money in the late 1800s. The care of horses during ice road operations required constant attention. The horses would be fed heavily, perhaps 30 pounds of hay and 10 pounds of grain per day, for a large draft horse doing hard work. They'd need access to water, though getting water on a frozen lake required drilling through ice. The horses would be checked daily for injuries, especially hoof problems and harness sores. A lame horse on a remote ice road was a serious problem that could delay operations. The shoeing of horses for ice work used special horseshoes with calks, sharp projections that provided traction on ice. The caulks might be removable so the shoes could be used on different surfaces, or they might be permanent for horses dedicated to ice work. The shoeing had to be perfect, because a thrown shoe 20 miles from shore could leave a horse unable to work and the entire team compromised. The most dramatic transportation over ice was moving locomotives. A locomotive might weigh 30 tons or more. Getting such a weight across lake ice required careful planning and specialized techniques. The locomotive couldn't travel under its own power. The vibration and concentrated weight on the wheels would stress the ice dangerously. Instead, the locomotive would be placed on a massive sleigh or wooden platform that distributed its weight over a large area. Then teams of horses, sometimes 20 or 30 horses, would pull the sleigh across the ice at a walking pace. The crossing of Lake Champlain by locomotives in the 1850s, during construction of the Rutland Railroad, is documented in contemporary accounts. The locomotives had to cross from Vermont to New York, and rather than dismantling them and shipping them by boat, the railroad chose to move them across the frozen lake in winter. The crossings were done in February and March, when ice was thickest. Each locomotive was placed on a reinforced wooden platform that spread its weight over about 200 square feet of ice. Teams of horses pulled the platforms across the 10-mile width of the lake. The crossings took most of a day and required constant monitoring of the ice. Another documented use of ice roads for railroad equipment was on the Canadian Pacific Railway construction in the 1880s. The railroad was being built across the Canadian prairies and through the wilderness north of Lake Superior. During winter, supplies were hauled across frozen lakes and rivers that would have been impassable in summer. The ice roads allowed the railroad to position materials and equipment at construction sites months before summer construction could begin. This advanced positioning was critical to maintaining construction schedules. Among the workers involved in ice road transportation was a man named Lars Johansson, a Swedish immigrant who worked as a teamster hauling railroad supplies in Wisconsin and Minnesota from 1872 to 1895. Johansson's diary, preserved by his family, describes the work and the dangers. From February 1878. We are hauling rails across Lake Superior ice. The lake is frozen solid. The ice is over 3 feet thick, but standing on it, knowing there is deep water beneath, is terrifying. We haul loads of rails from the dock to the construction camp 20 miles away. Each load is perhaps 2 tons. My team of 6 horses pulls the sleigh. We travel slowly, watching for any sign the ice is weak. Yesterday, a sleigh broke through on a different route. The driver and horses were lost. We found the hole. The ice was thin there from a current beneath. Now we are more cautious. Johansson's diary also describes the organization of the ice road. There are perhaps 50 teams hauling constantly. We travel in sequence, keeping space between sleighs so the weight is not concentrated. The route is marked with flags. We start before dawn and work until dark. Each trip takes most of a day, 20 miles out, unload, 20 miles back. In good conditions, 1 trip per day. In storms or when ice conditions are poor, we might make only half a trip or none. Another entry from March 1878 describes a close call. My sleigh broke through the ice today. We were perhaps 10 miles from shore. The ice gave way beneath the runners. The sleigh sank into water up to the load bed. My horses were in water to their bellies, struggling to keep footing. I jumped clear and pulled the horses forward onto solid ice. The sleigh was stuck, partially submerged. Other teamsters came to help. We unloaded the rails onto the ice to lighten the sleigh. Then, with multiple teams, we pulled the sleigh from the hole. The rails were lost, sunk to the lake bottom. I was lucky to escape with my life and my horses. 2 other men were not so lucky this winter. They went through thin ice and drowned before help could reach them. Johansson's diary entries from later in his career describe becoming more comfortable with ice road work. After 5 winters on ice roads, I no longer feel the fear I once did. I understand ice now. I can read it, see the signs of good ice and bad. I know when to proceed and when to stop. But I never forget the danger. Every day on ice is a day when death is possible. I have seen too many men and horses lost to ever become careless. Another documented worker was Michael O'Connor, an Irish immigrant who supervised ice road operations for the Canadian Pacific Railway in Ontario in the early 1880s. O'Connor's letters to the railway company, preserved in archives, describe the logistics and challenges. From February 1882, we have established ice roads across 3 lakes, totaling 45 miles. The ice thickness ranges from 30 to 42 inches. We have tested the routes with progressively heavier loads. Today, we successfully moved a locomotive across the largest lake, 15 miles from loading point to construction camp. The locomotive was placed on a specially built platform that distributed its weight over approximately 300 square feet. We used 28 horses in 7 teams. The crossing took 9 hours. The ice showed no signs of distress, though we heard constant cracking sounds that unnerved some workers. This success demonstrates we can move any equipment needed for construction. O'Connor's letters also describe problems and setbacks. We lost a loaded sleigh and team yesterday. The ice appeared solid, but there was a weak spot we had not detected. The sleigh broke through suddenly. The driver, Patrick Sullivan, was thrown clear and survived, but the 6 horses pulling the sleigh went into the water and were lost. We attempted rescue, but the cold water and the weight of their harnesses pulled them under. This is the 3rd team lost this winter. Each loss cost the railway $600 for horses, plus the value of cargo. But we have no alternative. Without ice roads, we cannot position the supplies needed for summer construction. A 3rd documented worker was Olaf Lindstrom, a Norwegian immigrant who worked as an ice road route scout and tester in Minnesota in the 1880s and 1890s. Lindstrom's job was to walk the ice routes before heavy hauling began, testing ice thickness and marking safe paths. His account, recorded in an interview in 1920, describes this specialized work. According to the interview, I would walk the entire route, sometimes 30 or 40 miles, carrying an ice auger. Every few hundred feet, I would drill through the ice and measure thickness. I would mark the ice with colored flags, blue for safe, yellow for caution, red for danger. In areas where ice was thin, I would find an alternate path or recommend delaying until more freezing occurred. My judgment determined whether operations could proceed safely. It was responsibility I took seriously because men's lives depended on my assessments being correct. Lindstrom described the factors he considered. I looked for clear blue ice, which is strongest. White ice I distrusted. It contains air and is weaker. I avoided areas where I could see cracks, unless the cracks were clearly frozen solid. I stayed away from areas where I knew there were currents or springs beneath. I checked the ice at different times of day because temperature affects strength. And I always gave conservative estimates. Better to be overly cautious than to lose men and horses to thin ice. He also described close calls. I broke through the ice 3 times during my years as a scout. Twice I was in shallow water and could wade out. Once I was in deep water and barely escaped. I was testing ice on a lake I thought I knew well, but there was a spring I had not detected. The ice gave way beneath me. I went into water so cold it stopped my breath. I managed to grab the edge of the hole and pull myself out. My clothes froze solid within minutes. I was 2 miles from the nearest shelter. I walked as fast as I could, knowing if I stopped I would freeze to death. I reached the shelter barely conscious. They stripped my frozen clothes and wrapped me in blankets. I survived, but lost 3 toes to frostbite. After that, I was even more cautious about testing unknown ice. The risks of ice road travel were constant and real. The main danger was breakthrough, when the ice failed under load. In shallow water, a breakthrough might mean a soaking and the loss of cargo, but survival. In deep water, breakthrough was often fatal. The cold water would cause hypothermia within minutes. Wet clothing would be impossible to remove. Even if you escaped the water, you'd be miles from warmth in freezing conditions. Many teamsters who broke through drowned or froze to death before rescue could arrive. The organization of large-scale ice road operations required careful management. For a major railroad construction project, there might be hundreds of loads that needed to be transported over several months. The operation would have a superintendent who would plan routes, monitor ice conditions, schedule loads, and coordinate the teams. Daily ice thickness measurements would be taken and logged. Weather forecasts, primitive but available, would be considered. The timing was critical because spring breakup could come suddenly, ending the hauling season. The ice road season typically ran from January through March in the northern states and Canada. Earlier than January, the ice might not be thick enough for heavy loads. Later than March, spring warming would weaken the ice dangerously. The season might be only 8 to 10 weeks for heavy hauling, which meant operations ran intensively during that period to move maximum material before the ice became unsafe. The typical day on an ice road hauling operation started before dawn. The teamsters would feed and harness their horses. They'd check their sleighs and loads. At first light, the convoys would begin moving. The loaded sleighs would travel out to the construction site, unload, and return empty for another load. A 20-mile route might allow one round trip per day. Shorter routes might allow 2 trips. The pace was dictated by ice safety. Traveling too fast would stress the ice through momentum and vibration. The horses used for ice road hauling were typically large draft animals: Percherons, Belgians, Clydesdales. These horses could pull enormous loads and had the temperament to work on ice without panicking. The teamsters developed strong bonds with their horses because their lives depended on the animal's performance. A horse that panicked on ice could cause a disaster. A horse that balked at the wrong moment might delay a convoy and expose everyone to increased risk. The loading and unloading of sleighs was done carefully to maintain balance. An improperly balanced load could shift during travel, potentially causing the sleigh to tip or creating uneven ice loading. The rails or ties would be stacked methodically and tied securely. At the construction site, the unloading would be done with care to avoid damaging materials and to ensure the sleigh remained stable until unloaded. The construction sites, supplied by ice roads during winter, would stockpile materials through the ice road season. By March, the site might have months' worth of rails, ties, and equipment positioned and ready. When spring came and ice roads disappeared, construction could proceed using the accumulated materials. This advanced positioning was often critical to meeting construction schedules because summer transportation was slower and more expensive. The economics of ice road transportation were favorable compared to alternatives. Moving a ton of materials 20 miles over an ice road might cost $1 or $2 in teamster wages and horse feed. Moving that same ton by wagon over rough forest roads in summer might cost 10 times as much due to the difficulty of the route and the time required. For railroad companies operating on tight budgets, the winter ice roads were essential to economic viability. The crossing of wide lakes required staging points where teams could rest. For a 40-mile crossing, there might be stations every 10 or 15 miles where fresh horses could be obtained and teamsters could warm up. These stations were simple shelters, perhaps just walls and a roof with a stove, but they were critical for safety. A teamster caught in a storm 20 miles from shore with exhausted horses might not survive without a station to provide refuge. The storms during ice road operations were dangerous. A winter storm could reduce visibility to near zero, create drifting that covered the marked route, and produce extreme cold that endangered both humans and horses. The protocol during storms was to stop and shelter if possible, but if caught in the open during a storm, teamsters would have to keep moving to avoid freezing, trying to maintain their heading despite poor visibility. Among the documented ice road operations was the construction supply for the Duluth and Iron Range Railway in Minnesota in the 1880s. This railroad was built to carry iron ore from the Mesabi Range to Lake Superior ports. The construction required moving massive quantities of materials through heavily forested and swampy terrain. During winter, ice roads across the numerous lakes in the region were used to position materials. Contemporary accounts describe convoys of 50 to 100 sleighs moving simultaneously, transporting thousands of tons of rails and ties over the several months of ice road season. The specific numbers from the Duluth and Iron Range operation are documented in company records. During the winter of 1883 to 84, the company established ice roads across 7 major lakes, totaling over 60 miles of ice highway. Over 12 weeks, from January through March, they transported approximately 3,000 tons of steel rails, 7 million board feet of ties, and numerous pieces of construction equipment. This required over 4,000 individual sleigh trips. The operation employed approximately 100 teamsters, 300 horses, and 50 support workers who maintained routes, operated staging shelters, and coordinated logistics. The cost of the ice road operation was approximately $20,000 for the season, about $600,000 in modern currency. This included wages for workers, feed for horses, equipment, and staging shelter construction. By comparison, moving the same materials by wagon over summer roads would have cost an estimated $100,000 and taken far longer. The ice roads saved the railroad $80,000 while also enabling an earlier construction start in spring. Another major ice road operation supported construction of the Canadian Pacific Railway through the Lake Superior region in the early 1880s. The terrain north of Lake Superior was some of the most difficult ever encountered in railroad construction. Rock cliffs, deep forests, and hundreds of lakes. During summer, progress was slow and expensive. But during winter, the frozen lakes provided natural highways. Supplies were moved from Thunder Bay across frozen lakes to construction camps dozens of miles inland. Without these ice roads, the construction schedule would have been impossible to meet. The Canadian Pacific Ice Road operations from 1882 to 1885 were massive. The company established ice roads across Lake Superior itself, crossing from the Ontario shore to islands and back to the mainland, creating a network of routes totaling over 200 miles. The routes were marked with poles every quarter mile to guide teams even in poor visibility. The company built warming shelters every 10 to 15 miles, simple structures with stoves where teamsters could warm up and rest horses. The tonnage moved over Canadian Pacific ice roads during those 4 winters was extraordinary. Company records document movement of over 15,000 tons of rails, 20 million board feet of ties, 60 locomotives, hundreds of rail cars, and countless tons of other supplies. The operation required coordinating hundreds of teams operating simultaneously across multiple routes. The logistics management, ensuring materials arrived at the right camps at the right times, was complex and required dedicated staff and communication systems. The communication along ice roads used a relay system. Riders on fast horses would travel the routes carrying messages between shore bases and camps. In critical areas, signal flags visible from observation points allowed for simple messages about ice conditions or emergencies. The lack of rapid communication meant that problems, a storm closing routes, a breakthrough requiring detours, might not be known for hours or days at distant parts of the system. The recovery of materials from breakthrough incidents was sometimes attempted if the water was shallow enough. Grappling hooks and chains would be used to locate and snag the sunken materials. In water less than 20 feet deep, recovery was often successful. In deeper water, the materials were simply abandoned. The sunken rails, ties, and equipment became permanent lake floor features. To this day, divers exploring northern lakes occasionally find 19th century railroad materials lying on the bottom, remnants of ice road breakthroughs. The insurance of ice road operations was difficult because of the high risks. Some railroad companies operated their own ice roads and self-insured, accepting losses as part of operations. Others contracted with independent teamsters who bore the risk themselves. The loss rates varied by season and conditions, but might be 5 to 10% of materials transported, meaning for every 100 tons moved, 5 to 10 tons might be lost to breakthroughs or other incidents. The record-keeping for ice road operations was detailed out of necessity. Every load had to be tracked: what it contained, which team transported it, when it departed and arrived, and whether it reached its destination safely. This documentation was essential for managing the complex logistics and for accounting purposes. The records that survive provide detailed insights into operations, including the losses and the costs. The seasonal variation in ice road operations meant that conditions changed dramatically over the season. Early winter ice roads in January might operate under ideal conditions: thick ice, cold weather, good visibility. Late season operations in March faced warming temperatures, thinning ice, and the constant threat of sudden breakup. The productive period was often only 8 to 10 weeks when conditions were optimal. Before and after this window, operations were risky and limited. The technique of reinforcing ice for heavy loads was sometimes employed for especially heavy items or weak ice conditions. Water would be pumped onto the ice surface and allowed to freeze, creating additional ice thickness. This could be done repeatedly to build up ice to 4 feet or more in critical areas. The flooding technique was labor-intensive, but could make the difference between safe transport and dangerous overloading. The breaking up of ice roads in spring was sudden and dramatic. Warming temperatures would weaken the ice from the top and bottom simultaneously. The ice that had been 3 feet thick and solid could become unstable within days. The end of the ice road season was determined conservatively. Operations would stop when ice conditions became questionable, even if the ice still appeared solid. The risk of late season breakthrough was too great. There are documented cases of entire convoys of sleighs breaking through weakened spring ice with catastrophic results. In March 1886, a convoy of 12 sleighs carrying railroad equipment on a Michigan lake broke through when the ice failed suddenly. 8 teamsters and over 40 horses were lost. The incident happened in late March when the ice road should have already been closed, but pressure to move materials before spring had caused the superintendent to approve continued operations, despite warnings from experienced teamsters. The transition from ice road transportation to other methods came gradually as railroads were completed and provided alternatives to ice roads. But even after railroads existed, ice roads continued to be used for construction of branch lines and for hauling materials to remote locations. The technique remained viable well into the early 1900s in some regions. The logging industry also made extensive use of ice roads, using the same techniques as railroad construction. Logs would be hauled across frozen lakes to sawmills. The ice roads allowed access to timber stands that would be unreachable during other seasons. This parallel use of ice roads by loggers meant that expertise in ice road operations was widely available in timber regions where railroads were being built. The cultural impact of ice road operations was significant in northern communities. The winter hauling season provided employment during months when other work was scarce. Teamsters could earn good wages during the 10 to 12 weeks of ice road season, perhaps earning as much in 3 months as they might earn in 6 months of summer farm work. The ice roads became part of the economic rhythm of these communities. The modern concept of ice roads, used in Alaska and northern Canada for accessing remote mines and oil fields, descends directly from these railroad construction ice roads of the 1800s. The techniques are fundamentally the same. Wait for adequate ice thickness, mark and prepare the route, move loads carefully while monitoring conditions, and stop operations when ice weakens in spring. The main difference is that modern ice roads use trucks instead of horse-drawn sleighs, but the principles remain unchanged. The documentation of ice road operations exists in company records, construction reports, and photographs. The photographs are particularly striking, showing locomotives on lake ice, long convoys of loaded sleighs stretching across frozen expanses, and the preparation work of clearing and marking routes. These images document an extraordinary transportation method that seems impossible, but was actually routine for several decades of railroad construction. The workers who operated ice roads, teamsters like Lars Johansson and the hundreds of others whose names weren't recorded, accomplished something that required both courage and skill. They moved millions of pounds of material across frozen lakes, risking their lives on ice that could fail catastrophically at any moment. They worked in brutal cold, often in storms, always aware that a breakthrough meant probable death. And they did it because it was the only practical way to supply railroad construction in remote locations, and because the pay was good enough to accept the risk. The legacy of ice roads in railroad construction is the railroads themselves. Many northern railroads were built using ice roads for materials transportation. Without this technique, construction would have been slower and more expensive, perhaps prohibitively expensive in some cases. The railroads that connected remote regions to the broader economy, that opened up timber and mineral resources, that enabled settlement of northern areas. Many of these railroads were built using materials hauled across frozen lakes by horses and men who understood ice. Today, most people traveling by train or car across the northern states don't think about how the railroad was built or how materials were delivered to remote construction sites. But if you're crossing a region with numerous lakes, it's likely that the railroad you're using was supplied in part by ice roads. The rails you're riding on might have been hauled across frozen lakes by horses 150 years ago. The ties beneath those rails might have been transported the same way. That entire infrastructure, taken for granted now, was created using techniques that sound impossible, but worked because people understood how to use winter as an advantage rather than an obstacle. 30 tons of locomotive on 3 feet of ice. Rails by the hundreds hauled across frozen expanses. Workers standing on lake ice in winter storms, coordinating the movement of materials that would build a railroad. It sounds like madness, but it was actually sophisticated logistics, using natural temporary highways that appeared every winter and vanished every spring. That's how America built railroads through wilderness, by turning winter and frozen water from obstacles into assets, and by having workers skilled and brave enough to make it work.